Transport Reform, who is here representing Georgia.
Thank you. So my name is Akila. I come from Reform Networks, and the topic is SRv6. Very short introduction. The topic is not very large, but I try to cover everything or the basics in the next 10 minutes. So I know that some of you are quite familiar with the culprit of the presentation, but I hope that I can shed some new things to at least some of you. Okay, so the main question, or the first question, is what is SRv6? And the background of SRv6 is as illustrated here. So we have been living in the traditional MPLS world for, I don't know, 25 plus years almost. And we all know that MPLS is good, it's well known, it's well supported, and so on and so forth. I personally love MPLS. I've been doing everything related to MPLS for almost all the time. But also we know that MPLS has its downsides. So that is one of the reasons why new things are created, because we see that something needs to be done to be able to do something better. And for this basic technology that we have now two different paths. So we have the evolutionary path and we have the revolutionary path. And the evolutionary path is towards the segment routing MPLS, and the revolutionary path is towards SRv6. And if we consider the development of these two different technologies, whether it's the evolutionary or revolutionary path, we see that everything started about 10 years ago, and now we are at a point where both technologies are used, at least to a certain extent, in different networks all over the world. So if we take a look at the current state of SRv6 globally, we can argue that it's somewhat used. It's not used very heavily all over the world, but somewhat used. And then there is still support for it from the vendor side. So the major networking equipment vendors are supporting SRv6, and also the IETF community, or the standardization community, is supporting SRv6 in providing the different documentation, the different standards, to be able to create the different services and to implement everything so that it's interoperable between the different vendors. If we take a look at the main documents for the SRv6, we can say that okay, it's divided into four major areas. We have the architectural documents that are covering what is actually happening, what are the needs, and how different things are put together. Then there are the data plane documents defining how to transmit data. There are the control plane documents defining how to find the control information, and then there are operational management documents. So the main question is, how does everything work? And we can say that SRv6 is yet another underlay-overlay mechanism. We have an underlay that is purely IPv6. So this is the last thing that is needed to be able to transfer totally towards IPv6. Just to say. Okay, but anyhow, the underlay network is pure IPv6, and we need a normal traditional IGP routing in the underlay. So probably ISIS, or most of the users are running ISIS, but of course the other alternative is quite okay as well. We can also use external sources or policies, so some sort of a traffic engineering server is quite okay. And if we consider the underlay network, one of the things that it's not mandatory, but it's highly recommended, is that the prefixes used there are aggregated. And that is one of the upsides of the whole technology, so that we can use only pure IPv6 network, and we can also reduce the amount of control information by using the application. And the overlay network is whatever we want to do. So traditional mechanisms apply, but we can also use a little bit newer mechanisms And especially we can use service training mechanisms, because if you consider SRv6 in the end, what it is it's a way to do network programming. And the network programming in this sense means that we can tell to the network nodes how to traverse, we can tell inside the packet how to traverse the network. And that is one important issue in SRv6. We can tell that, okay, this packet needs to go via this router, via this router, via this router towards the end of the line, or this packet needs to go via, for example, firewall or other service element within the network. How does it do that? It's done via so-called segment identifiers. And segment identifiers are presented via SRv, in this SRv6 technology via IPv6 extension headers. And I will come back to the extension header in the next slide, but first a few words about the SIG, the segment identifier. There are a couple of terminological issues related to that. We are talking about the segment identifier, we are talking about segment identifier prefix, and we're also talking about locator. And this slide tries to clarify these terminological issues. So basically, the segment identifier prefix is the IPv6 address space that is used for the SRv6 purposes. So we can use either the unique local addresses or global unique addresses for that. The unique local addresses are, of course, the benefit is that it's easier to prevent them from leaking from one network to another. But the downside is, of course, that if you're using the unique local addresses and then you're merging different networks, there might be some overlapping issues. So both alternatives are quite okay. Then each of the nodes in the network that are participating in the SRv6 locator, one or more locators are located in that device. So basically, in the normal case, we allocate one locator, but if there is a need to have other multiple services or things like that, then we can use multiple locators in one node. And as said, the locators are just normal IPv6 addresses, and they are routable in the network, and they are aggregatable within the network, and they are advertised by the normal IGP. The actual segment identifier then contains the instruction. So when we are talking about network programmability, it means that we are really telling to the network what is actually happening, and we are telling to the nodes what is actually happening there. So we are instructing the nodes, and the instructions go via the segment identifiers. And there's an example of that. So basically, the example here is that the segment identifier is a locator, and then 000A. And for that specific node, the 000A might mean format this traffic via nearest table 1. So there is an instruction that is given to the node, and similar kind of instructions can be then programmed, and similar kind of instructions can be then advertised throughout the network, and then create services on top of the SRv6 network. When we have, I'll come back to the last part, but when we have the segment identifier, the basic idea is to have and use extension header to IPv6. The extension header is called segment routing extension header, SRh, and the basic format is shown here. What is interesting to see here is that, of course, it has normal headers, 8 bytes altogether. And then it has segment list. And the segment list is used to instruct the packet how it traverses the network. And this is the basic case. This is the kind of an original idea of how things should be done. And here the issue is that each of the segment identifiers, each of the instructions here is normal IPv6 address, so it's 16 bytes. And if you consider that I need to give multiple instructions to the data packet, so for example, I have 6 different segment identifiers, it means that I have 104 bytes of segment identifiers, which is then relatively large amount of overhead in this. There are two things that need to be considered here, and the first one is, I'll come back to one slide. The first one is the last bullets. So in normal case, when we are talking about, for example, services over the SRv6 network, we are using only the normal IPv6 destination header. So everything is encoded into the normal destination header. But if we need to do something else in the network, then we need to use multiple segment identifiers, so multiple instructions. And in this case, we can use the so-called microseed or compressed seed, which just means that we are not using the full segment identifier function field, which is, well, it depends, but it's normally the last 64 bits of the IPv6 address. Instead of that, we can encode the instructions with shorter terms. So here's an example of using 6 seeds in the last bits of the IPv6 address. So that is a way to save space and then reduce overhead. Okay, so what can we do with the segment identifiers? As I said, it's that the segment identifier is a key for the network programmability. And this must not be confused with the network programmability as is touted by some vendors, where you are talking about network programmability in terms of netconf, restconf, and JSON and whatnot. But the network programmability here means that we are instructing the network directly via the data graph. So there are 2 different ways, two different things that we can do here. One is the network level functions, and the other are customer facing functions. Here's an example of using the segment identifiers. I will come back to the different ways to use the SRv6, but here's just an example of using the segment identifier. So the first is the P1 on the left, and P1 is then instructed to forward the traffic to P1. Then P1 is instructed to forward the traffic to P3 by the segment identifier, so by the instructions. Now there is a non-SRv6 node along the way, the P2. And in this case, P2 does not understand anything about SRv6, but since the instruction is just an IPv6 destination address, it can forward the traffic still to P3, which is then taking the instruction and seeing that, okay, this traffic goes to PE2, which is then instructed to process the last of the segment identifiers and then forward it whichever way is forward. So we have different kinds of SRv6 policy behaviors. We have headend behaviors, and then we have endpoint behaviors. The headend behaviors happen on the source node, and the endpoint behavior happens on the end node. And if you consider these different behavior styles, the headend behaviors normally are used for the network functions. So basically, as I said, there are 2 different variations. So we have the network functions, we have the customer functions, and the headend behaviors are mostly used for the network functions. For example, the topology independent loop-free alternate mechanism, which I will show a little bit later in the slides. And the endpoint behaviors are then used to steer the traffic in the edge of the SRv6 network. So we can use those to instruct the last node in the SRv6 network what to do with the data. And then there are some additional behaviors that are closely resembling what we are doing in the normal MPLS network. So penultimate hot popping, here it's penultimate segment pop, and so on and so forth. Here are some examples of the end behaviors. So what we have here, this is just a brief list of the examples. So if you take a look at the current state from IMS pages, there are maybe, I don't know, 50, 60 different end behaviors. But these are relatively easy to understand, and therefore I took these. So well, let's directly to NPTs and NPXs. So NPT4 and NPT6 are instructions how to forward the packet in the last node of the path. And DT4 means that, okay, forward it via IPv4 table lookup via ERF, basically. And this can also be translated that it's equivalent to per VRF label. And then DX is per CE label. So if we consider what is happening in the normal MPLS network, we can also forward per VRF or per CE in that. So same behavior, different kind and different style, but in the end, the data gets forwarded in the right direction. Okay.
Can I ask a question about the previous slide?
Yeah.
Sorry. So DX2, does it mean that there's an Ethernet packet inside the IPv6?
Mm-hmm. Yeah.
What's the next header for Ethernet header?
What's the
next header field value for Ethernet?
Don't remember by heart.
But there's
yeah.
Okay.
Yeah. Okay. So a few words about the services. First of all, the SRv6 services in the backbone. There are this slide shows just some examples of the possibilities in the network level. So already mentioned is the topology independent loop-free alternate. There's also a possibility to do micro avoidance via SRv6. Flexible algorithm is one of the possibilities. And then there are some other ways to enhance the functionality of the network via SRv6, but I just took an example of the topology-independent loop-free alternate and the flexible algorithm. So basically, TI-LFA, what it means in SRv6 is that SRv6 is able to provide 100% coverage of the network. In terms of link and node protection, and what is interesting and takes this apart from the traditional ways of doing this same thing is that SRv6 is now capable of programming the actual path, and therefore SRv6 is capable of preventing suboptimal routing in the network. So basically, what we see here. I don't know if you can disclose. Yeah. Okay. So what we have here is a network and core devices 2, 3, 6, and 7, and then we have edge devices 1, 4, 5, and 8. And if we consider what is happening here is that there is a problem, a link broken between 2 and 3, or in the original topology, the traffic flow in between 1 and 5 goes to from 1 to 2 and 2 to 3 and from 3 to 5. When the link is broken between 2 and 3, the classical loop-through fast route uses PE4, but we don't want the traffic to traverse the edge device. We want the traffic to traverse the core devices, and this is ensured, this is possible by using the SRv6. What is happening here is that SRv6 is automatically taking into consideration the post-convergence path, and to avoid the possible loops there, transient loops that happen when the IGP is recalculating and so on and so forth, what is happening is that the 2 is programming the data so that it traverses 6 and 7 and gets to 3. even though IGP sees that there might be problems. And once IGP converges, then what we see here is that the traffic goes naturally via R1, 2, 6, 7, 3, and 5. So that's the idea of using SRv6 in this case. Another example is the flexible algorithm. We can also call and talk about slicing in a network, but both terms are quite okay. So basic idea here is that we can create alternative paths with different properties throughout the network. And possibilities are, of course, the minimal delay is something that we always want to have. We can argue that a path that has the highest bandwidth is also nice to have. We can avoid certain links. Traditional examples include, for example, satellite links, and maybe also links that are very costly. But we can assign different constraints and different parameters to different links, and then the flexible algorithms are able to calculate the best possible paths. And there is a different separate RFC document that defines extensions to both ISIS and OSPF for to calculate these different constraint-based paths. But the basic idea here is that we can calculate the different paths, and then we can use the instructions. So we can use the segment identifiers to direct traffic through these different paths. And this is the thing that SRv6 is capable of doing. If you consider the traditional mechanisms of using the constraints and calculating the different paths that we have been able to do in MPLS networks as well, this is very much more simple to do in the end. Okay. So those are just examples of what can be done in the network level, and then of course we need to have some services towards customers. And in terms of services, we can use more or less all the traditional ways to create services as we have done previously. So there is not much different in that sense. Of course, we need to ensure that the devices are capable of understanding the SRv6 instructions. So to direct the data traffic from that comes into the next device towards a certain VRF or whatever construct is used. But anyhow, a separate RFC document, the PGP overlay services based on segment routing over IPv6, is defining both the traditional PGP-based layer 3 VPNs, the RFC 2547 and also the PGP-based eVPN constructs can be used on top of that. And in addition, the service elements can be inserted. So I said that we can run the traditional services on top of SRv6 network, but we can also create and deploy different service elements along the path. And this is based on the service function chaining architecture that IVDF has created, RFC 665. And here the RFC document defines the network service header, the NSH. And in SRv6 network, the NSH header is actually the segment identifier. So the segment identifier is used to steer the traffic through the network to a service element, and then from the service element forward wherever it is going. So both traditional services and a little bit easier way to do the service chaining is possible via SRv6. So as I said, very quick, very brief introduction to SRv6. Any questions? I'm not going to be here all night.
Are you going to stay for dinner?
Yeah, I'll stay for dinner. Yeah.
Okay, so if you don't have questions right now, then you can still ask them during dinner.
I have a comment.
Okay.
I'm really happy that we have come this far from 2025.
Yeah. Okay. Thank you.
Give a big hand to our two.